According to the National Electrical Code, several requirements must be met when installing electrical equipment. These include overcurrent protection, conductor sizing, and voltage drop limitations. The fuse disconnect must provide adequate overcurrent protection for the new equipment being installed. Conductors must be sized appropriately to carry the load current, with consideration given to any additional ampacity needed to compensate for voltage drop. The voltage drop along the conductors should not exceed 5% for feeders. Now let's consider a scenario involving a number 6 conductor running from a 208 volt 3-phase 70 amp source to a 3-phase 20 amp fuse disconnect, and then continuing from the load side of the 20 amp disconnect to a new piece of equipment. The total length of the run is approximately 35 feet, with 20 feet horizontal and 15 feet vertical, all installed in E&T conduit and protected from physical damage. Firstly, overcurrent protection. A 20 amp fuse in the disconnect provides overcurrent protection for a 20 amp load. Secondly, conductor sizing. For a 20 amp load on a 208 volt 3-phase system, the conductor ampacity should be at least 25 amps. This is calculated by multiplying the load current of 20 amps by 1.25. A number 6 conductor typically has an ampacity of 65 amps, which exceeds the required 25 amps. Thirdly, voltage drop. Using the NEC voltage drop calculation methods for EMT, the voltage drop for a 35-foot run of number 6 conductor carrying 20 amps is approximately 1.25%. This value is well within the allowable 5% limit for feeders. In summary, based on this analysis, the proposed solution appears to meet the NEC requirements for overcurrent protection, conductor sizing, and voltage drop. However, this assessment is preliminary. A qualified electrician should perform a thorough inspection and calculation to ensure full compliance before any installation work begins. It's crucial to understand each of these aspects in greater detail. Let's begin with overcurrent protection. Overcurrent protection devices, such as fuses or circuit breakers, are essential for safeguarding electrical circuits and equipment from excessive current flow. This excessive current can result from overloads, short circuits, or ground faults, all of which can lead to overheating, insulation damage, and potentially fire hazards. The primary purpose of an overcurrent protection device is to interrupt the circuit when the current exceeds a predetermined safe level. This interruption occurs rapidly, preventing damage to the conductors and connected equipment. The selection of the appropriate overcurrent protection device is critical and must be based on the ampacity of the conductors being protected and the characteristics of the connected load. The NEC provides detailed guidelines and tables to assist in selecting the correct overcurrent protection for various applications. For example, NEC Section 240.4b addresses the protection of conductors, specifying that conductors must be protected against overcurrent in accordance with their ampacities. Now let's delve into conductor sizing. The proper sizing of electrical conductors is paramount for ensuring the safe and efficient operation of electrical systems. Undersized conductors can overheat due to excessive current, leading to insulation breakdown, voltage drop, and potential fire hazards. Conversely, oversized conductors can be unnecessarily expensive. The NEC provides comprehensive tables, such as those found in Article 310, that specify the allowable ampacities of conductors based on their size, insulation type, and installation conditions. These tables take into account factors such as ambient temperature, the number of conductors in a raceway, and the type of raceway. The ampacity of a conductor is the maximum current, in amps, that it can carry continuously under specific conditions of use without exceeding its temperature rating. Several factors influence the appropriate conductor size for a given application. These include the load current, the ambient temperature, the type of insulation, and the length of the conductor run. For example, if a conductor is installed in a high ambient temperature environment, its ampacity must be derated to account for the increased heat. Similarly, if multiple current-carrying conductors are bundled together in a raceway, their ampacity must be adjusted to account for the mutual heating effect. Voltage drop is another critical consideration in conductor sizing. Voltage drop refers to the reduction in voltage that occurs along the length of a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction, reduce the efficiency of lighting systems, and lead to inaccurate readings from sensitive electronic devices. The NEC recommends that voltage drop should not exceed 3% for branch circuits and 5% for feeders. To calculate voltage drop, several factors must be considered, including the conductor's resistance, the length of the conductor run, and the current flowing through the conductor. The formula for calculating voltage drop is typically expressed as voltage drop equals current multiplied by resistance. The resistance of a conductor depends on its material, length, and cross-sectional area. The NEC provides tables that list the resistance values for various conductor sizes and materials. Now, let's look at the specific case mentioned earlier. A number 6 conductor is being used to supply a 20 amp load on a 208 volt, 3-phase system. The conductor run is 35 feet long, installed in EMT conduit, and protected from physical damage. Firstly, overcurrent protection. A 20 amp fuse in the disconnect provides adequate overcurrent protection for the 20 amp load. The fuse is sized to protect the conductors and equipment from overloads and short circuits. Secondly, conductor sizing. For a 20 amp load, the conductor ampacity should be at least 25 amps, which is 125% of the continuous load. A number 6 conductor has an ampacity of 65 amps, which is more than sufficient to carry the load current. Thirdly, voltage drop. Using the NEC voltage drop calculation methods, the voltage drop for a 35-foot run of number 6 conductor carrying 20 amps is approximately 1.25%. This calculation takes into account the conductor's resistance, length, and current. The voltage drop is well within the allowable 5% limit for feeders, ensuring that the equipment receives adequate voltage for proper operation. In this scenario, EMT conduit is used as the wiring method. EMT, or electrical metallic tubing, is a type of rigid metal conduit that provides excellent physical protection for conductors. It is commonly used in both exposed and concealed locations and is suitable for a wide range of applications. EMT is easy to install and can be bent and cut to fit various configurations. It also provides a continuous grounding path when properly installed. When installing EMT, it is important to use the correct fittings and connectors to ensure a secure and watertight connection. These fittings must be listed and labeled for use with EMT and must be installed in accordance with the manufacturer's instructions. Proper grounding is essential for the safe operation of electrical systems. Grounding provides a low impedance path for fault current to return to the source, allowing the overcurrent protection device to trip and clear the fault. The NEC provides detailed requirements for grounding electrical systems, including the size and type of grounding conductors, the methods for connecting to ground, and the bonding of metal enclosures. In a 3-phase system, such as the 208-volt system described earlier, the grounding requirements are particularly important. A 3-phase system typically has a neutral conductor that is connected to ground at the source. This neutral conductor provides a reference point for the phase voltages and helps to stabilize the system voltage. The grounding electrode system must be installed in accordance with NEC Article 250 and must consist of one or more grounding electrodes, such as a metal underground water pipe, a ground ring, or a rod or pipe electrode. The grounding electrode system must be connected to the building's metal frame, if any, and to the neutral conductor at the service entrance. Bonding is another important aspect of grounding. Bonding refers to the connection of metal enclosures, raceways, and other non-current carrying metal parts to form a continuous electrical path. This path ensures that all metal parts are at the same potential, reducing the risk of electric shock. Bonding is typically accomplished using bonding jumpers, which are short lengths of conductor that are connected between metal parts. The size of the bonding jumpers must be in accordance with NEC Table 250.102 Current. In addition to grounding and bonding, surge protection is another important consideration for electrical systems. Surge protection devices, or SPDs, are designed to protect sensitive electronic equipment from voltage surges caused by lightning strikes, power grid switching, and other transient events. SPD work by diverting the surge current to ground, preventing it from reaching the protected equipment. The NEC requires SPD to be installed in certain locations, such as at the service entrance and at sensitive electronic equipment. The selection of the appropriate SPD depends on the voltage and current rating of the electrical system and the type of equipment being protected. The installation of SPD must be in accordance with the manufacturer's instructions and the NEC. Regular inspection and maintenance of electrical systems are essential for ensuring their continued safe and reliable operation. Inspections should be performed by qualified electricians and should include a visual examination of all components, testing of overcurrent protection devices, and verification of grounding and bonding connections. Maintenance should include tightening loose connections, cleaning equipment, and replacing worn or damaged components. The NEC provides guidelines for the inspection and maintenance of electrical systems. In addition to the NEC, other codes and standards may apply to electrical installations. These include local building codes, fire codes, and equipment listing standards. It is important to be familiar with all applicable codes and standards before beginning any electrical work. The NEC is updated every 3 years, so it is important to use the latest edition. The NEC is available for purchase from various sources, including the National Fire Protection Association, or NFPA. It is also available online through various subscription services. The NEC is a complex and comprehensive document, so it is important to seek guidance from qualified professionals when interpreting and applying it. Electrical work can be dangerous, so it is important to take all necessary precautions to protect yourself and others. Always to energize circuits before working on them, use appropriate personal protective equipment, and follow safe work practices. If you are not qualified to perform electrical work, hire a licensed electrician. In the scenario described earlier, the proposed solution appears to meet the NEC requirements for overcurrent protection, conductor sizing, and voltage drop. However, it is important to note that this is a preliminary assessment, and a qualified electrician should perform a thorough inspection and calculation to ensure compliance before installation. The electrician should verify the ampacity of the conductors, the size of the overcurrent protection device, and the voltage drop under actual load conditions. They should also ensure that all grounding and bonding requirements are met and that the installation complies with all applicable codes and standards. In conclusion, understanding and complying with the NEC is essential for ensuring the safe and reliable operation of electrical systems. The NEC provides detailed requirements for overcurrent protection, conductor sizing, voltage drop, grounding, bonding, and other aspects of electrical installations. By following the NEC, you can help to prevent electrical hazards and protect people and property from harm. And never undertake electrical work if you don't have the adequate experience. When working on electrical systems, it's always better to be safe than sorry.